What's up, calculus students? Mr. Messer coming at you. We're going to go over the 2025 free response questions and answers just released today. I'm going to give you my overall perspective of the test, what I thought was good, maybe bad, and give you all the answers. We're doing the A-B test. We're starting with question number one, which talks about invasive species of plants. They're giving you equation for C and its derivative C prime. You need to know that C is a position. It's a number of acres. C prime would be the rate of change of the position. And let's go through the parts. So, first part was find the average number of acres affected. So, this is the average acreage. The average acres would be the average C, not the average C prime, because C is going to be acres and C prime is acres per week. To find the average of something, I want to accumulate that something and divide it by the integral, and boom, I'm going to get my answer. Now, this is the first test that we were able to use Desmos, so some things we need to worry about is making sure we type in C and C prime and that we can see them and accumulate them. And when you try to graph C prime, they won't let you. So this is why, just heads up, I tell my students maybe graph V, V of T, V sub C, and you can see the velocity as the derivative. We've been using velocity as a different word for a derivative. And that's a good way to see it, but I would have just accumulated from 0 to 4C and divide that by 4. And that's how you get your answer. 2.778. Cool. And then the next question was to find when the instantaneous rate of change equals the average rate of change. This is a mean value theorem question. Instantaneous rate of change is a derivative, so I'm going to look at C prime. Average rate of change is slope of a secant. They're both slopes. This is the slope of the tangent. This is the slope of the secant. This is mean value theorem, only they don't specify this is a mean value theorem question. So you can find the average rate of change by doing C4 minus C0 divided by 4, or 4 minus 0. That's the average rate of change. And then we know that the instantaneous rate of change is C prime. I want to figure out when C prime equals that number. How do I do that? I will graph Y equals that number. I will make sure I'm just looking at C prime. I will find the intersection. We're looking from 0 to 4, which means I'm not going to include, maybe I want to include 0, but usually we just look at inside the interval. So I don't know. Would we include 0? Is that really an intersection? I don't even think that's an intersection. Yeah, no, I would just include this point right here, which is the intersection 2.154. Okay, that was part B. Probably the first part was worth 3 points potentially. Second part worth maybe 2 or 3 points. I think this question number one was the hardest question of the entire test. Part C says, okay, imagine that the invasive species continues to spread according to the model given for all of the times. Write a limit expression that describes the end behavior of the rate of change in the number of acres. So we are looking for the end behavior of the rate of change. It's the end behavior of C prime. I want to look at the limit as t approaches infinity of C prime. Now, this is probably worth 1 point, probably looking at C prime. And you could literally just look at C prime and look at the end behavior of C prime by just kind of zooming out and being like, well, my C prime values are getting closer and closer to 0. Just writing 0 probably would have gotten you some credit. Let's go home. Probably would have gotten you some credit, but full credit, they wanted that limit expression and to say that the limit equals 0. Let me go to part D. This question bothered me the most, and I'll tell you why. So we have this function a that's defined by, the amount of acres minus this accumulation of this thing. Okay, and they are saying this is a new function a that we are going to use from 4 to 36. And the question is, when does a attain its maximum value? The reason why this question upsets me is the following. And I'm just going to get rid of everything that we have and just look at, well, I do need C. So let's bring C back. Okay, cool. I'm going to say, hey, let me look at A. A of t equals c of t minus the integral from 4 to t of 0.1 times the natural log of x dx. You could type that in to Desmos just as you see it, and you can see where the maximum is. And that is the answer. But this, which is why this upsets me, because this is the first time really like using TI-84 calculators, we haven't been able to graph accumulations because it takes a calculator so long to accumulate. It's not worth the effort to try to graph an accumulation. But since Desmos is so quick, the accumulation can be graphed and you can analyze it. And this is like the position function for the total of acres that the species has invaded. Um, yeah, the acres of fruit grove that's been infested. But this is not very calculus in its nature. We don't want to just say, there's the max. How do we find maxes and mins? How do we figure out when something's increasing or decreasing? We should be looking at the derivative. And the derivative is c prime minus 0.1 lnt. And I kind of walk through why it is. It's using the second fundamental theorem of calculus that's saying the accumulation of this is really like the antiderivative of t minus the antiderivative of 4. And when you take the derivative of that, you just get c prime minus the stuff on the inside with t's. So I would have actually said the velocity of A is equal to c prime, which is the velocity of c, which I will put down. Maybe this would have been a good V1, V2 situation. Maybe I say it's V1, 25 plus t squared. And obviously you don't have to do this. You can type this into the integral. But the velocity of 1, and you can see it's on top of the graph, minus 0.1 times the natural log of t. And we really only want this for t's greater than 4. And we're really going from 4 to 36. I'm going to hide, well, I'm going to keep that, but I'm going to hide the c prime. And I get this graph right here. Okay. Now look, this is the max. That is when my derivative changes sign from positive to negative. This is what they wanted. They wanted you to find the derivative. They wanted you to find the zero. They wanted you to justify maxes. This is what I'm guessing by talking about the signs of the derivative. The derivative is positive from 4 to 11.441. The derivative is negative from 11.441 to 36. Therefore, the max has to be here. And you don't have to check any endpoints or anything. As long as we go out to 36 and the derivative stays negative, this confirms that it has to be the max. And there's really another question later in the test that talked about a overall max or an overall min, but you didn't have to really check candidates here either, as A must be increasing, A must be decreasing. 11.441 has to be the max as long as you write what your derivative does somewhere. As long as you put your derivative down, you're going to get full credit. I can imagine this being very controversial in terms of the points that can be earned. Maybe get 1 point for identifying this value, maybe get 1 point for having the derivative and 1 point for that. Okay. I thought this is the hardest question. And if that's the hardest question, then that's not that bad. Okay. We move on to question 2 on the A/B test. And I'll be back in just a second. Cool. Very simple function, f and g. F and g can be graphed easily. This is very surprising to see an area volume on a calculator section. To be honest, it's been a while since an area volume has been on a calculator section. It's such a nice, easy intersection. So nothing crazy going on with finding intersections. And we start off with the area. I like to tell my students to accumulate heights times widths. So I like to either say h equals g minus f, the top minus bottom is the height at any given x, and you're going to accumulate those g's from those h's from 0 to 3. So my students like to put h as g minus f. or they could put it in terms of the function. And I say accumulate from 0 to 3 your heights times your widths to get your area. Okay, and that's the correct answer. Part B, we got region R is a base of a solid. We're putting cross sections perpendicular to the x-axis. We got rectangles. We have a height x. Now this is tricky having a height x. Now I kind of drew it here, but I also put it here. It's like, imagine this is coming outside my paper. We have this height of my rectangle. We have this skinny width of my rectangle. And then coming out of my paper is this length x. So it all depends on the x coordinate, what this length is going to be. So really, you just have to accumulate your x times your h's. So all I have to do is come back to my calculator and just type in x right into there. And boom, I got 7.704. So that was pretty easy if you just pick that up. Spinning, always tough for students to remember how to spin things. Now let's think about spinning. We are going to look at the line y equals -2. This is going to get spun around this line. So we create this three-dimensional object, and this three-dimensional object is going to kind of look cylindrical. We're going to have a bunch of like circles because we're spinning. Well, the key concept is to take a rectangle, spin that, create a cylinder. Cylinders right here that have circles on the side where we have a radius and a height, but the height is very small. The volume of a cylinder is pi r squared h. Well, pi, here's r squared h. We just need expressions for r. Well, we have an outer radius, which would give us everything. But then we have these inner radiuses of this negative space, this hole. So I have an expression for the outer radius and the inner radius. I remember that pi r squared h would be pi r squared times dx if these cylinders are very, very skinny. And here's my answer. I'd either have pi 0 to 3 of r, big R squared minus small r squared, or you could factor out the pi, factor out the dx, and you have r squared minus r squared. Very easy. My students are going to just say big R is g of x minus 2, minus -2 or plus 2. Small r is f of x minus -2. And I will pi integrate from 0 to 3, my outer r squareds minus my inner r squareds, with the only trick being put this in parentheses because we factored out the pi and the dx. And that's how you get it if you were my student, or you would change this to plus. Okay, very simple. It's very nice to have Desmos to have this, so you don't have to, so like you're using notation, you're using concepts to help lead the way versus anything else. Okay. And then part D was an interesting question. It says, when is F parallel? When is the graph of the tangent to F? When is the line tangent to F parallel to line tangent of G? It's very simple. You have to think about what parallel lines have in common. Parallel lines, the slopes are equal. The slope of f, when does that equal the slope of g? Well, obviously the derivative of f, and the derivative of g is what you're trying to find. Well, they gave you the derivative of g. Thought that was very soft that they gave you the derivative of g. Maybe it's so they can grade it easier, so they don't have to check and like see what their wrong answer, if they got the wrong answer correctly or something. I just think they're making this easier to grade. They gave you the hard derivative. All they asked you is for the easy derivative. You had to find that f prime was 2x minus 2, and you said 2x minus 2 equal to 1 plus pi cosine pi x. You would just graph f prime and g prime, see where they intersected. It was very easy. So it's probably one of these points right around here. I guess that they're the same. 0.65. So I feel like, is that right? I mean, it must be. Just gonna do it real quick. And you know what's great? You could actually graph y equals f prime and y equals g prime. This is one way around it. And you could find what f prime equals g prime from, 0.675. Yeah, look at that. So like you actually didn't have to find the derivative. So I would be interested to see, did you find the derivative? Did you have to find the derivative? Or could you have just graphed the derivatives using Desmos. You're good. Cool. And there's the calculator section. Very interesting to see a area volume as question number 2. It's been a while since we saw area volume. Hopefully my students were ready. And I thought question number 1 was a good challenging question, which a lot of students might have gotten tripped up on. Now, starting on the no calculator part, we had a good AB/BC question where it was important not to simplify. Okay. Especially once we started doing Riemann sums and stuff like that. We got this words per minute situation. I was supposed to show you the questions at the beginning if you paused. Here's question number 2. If you wanted to pause and do question number 2, there it is. Now let's go to question number 3. Here's question number 3. It talks about a student reading a book in words per minute. One of my students says it's very interesting how much faster they ended up reading in this interval than they started. I said maybe they were just like warming up and they were getting into it. Anyways, it's an interesting question. The key to the calculus question is the fact that it is a rate of change. It's words per minute, so it belongs in a derivative line, which means if you accumulate it, you'd get words. If you take the derivative of it, you'd get a rate of change of a rate of change, which is an acceleration or words per minute squared. So r prime of 1 using the average rate of change of r from 0 to 2, it's very clear what they wanted you to do, should be 5 words per minute squared. They didn't have you explain that the words per minute are increasing or the rate that the student is reading is increasing. They just said, get that. I mean, pretty straightforward and very easy. Then we have must there be a point where the rate of which we are reading is 155 words per minute? And the answer is like, obviously, we're going to go from 150 to 162. We have to pass 155. But we needed to talk about how this function is differentiable, therefore continuous, and that the intermediate value theorem guarantees that this value must be true. If your function is continuous, you're connecting 2 points, you must pass through all the y values. So I kind of was more specific. I said there's got to be a c between 8 and 10, for which r of c is 155. Since r is differentiable, that means it's continuous. Part C, they didn't even ask you, what does this mean? I was upset that they didn't ask you what this meant. They asked for the trapezoidal Riemann sum, so you just use the formula for a trapezoidal Riemann sum. 1/2 the length of the base times the sum of the 2 heights. So make sure you understand the lengths of your bases. It goes from 2 to 6 to 2. And make sure you double your heights when you need to double your heights. But what I wanted is like, what does that mean? It's like the total words that this student read over the 10 minutes. I wanted that. Why didn't they ask you that question? I don't know. A little bit soft. Words read over 10 minutes. I feel like my students are ready for that. Apparently I didn't need to get them ready for it. They just needed to just blindly do the Riemann sum and not know what it meant, which is, it got upsetting for me. I'm venting. Moving on. A teacher also started reading. The teacher read at a rate by W in words per minute. How many words has the teacher read by the end of the 10 minutes? So I guess maybe the fact that they didn't ask it for C, they are kind of asking it here for D. W is in words per minute, which means if you accumulate W, you get words. We want to accumulate W from 0 to 10, but we don't have our calculator. What are we supposed to do? You need super W of 10 minus super W of 0. That's what I call the antiderivative of W, especially when W is already a capital letter, you know? So I said super W of T is that. And when we subtract, we don't need the plus C. Don't simplify, just plug in 10. And when you plug in 0, you get 0. And this is the amount of words read. And if you simplified, you wasted time. Then we go to our function analysis question. Not surprising. What it was surprising was that it's so simple. I think it's good that the graph wasn't crazy. We are starting at 6, which is different, but you know, it's not a hard one. The areas are fine. We're not shifting things up or down. It's a lot easier than a lot of previous years. All you needed to know is that when you take the derivative of the integral, you just get f. So it turns out G is the graph of a derivative. Okay. Sorry for not showing you this question. Let me show you this question. If you want to pause and do this question, this is the question number 4. Question number 4. Okay, cool. So very straightforward function analysis question. You need to know that G prime is equal to F. This needs to be written down somewhere on your paper to get a point. And then that means G prime of 8 is F of 8. F of 8 is 1. Done. Part B. Where do we have points of inflection? Well, I like to do the second derivative sign analysis. Well, if G prime equals F, G double prime equals F prime. That's important to write down somewhere. And as G double prime changes sign, F is going to change directions. G is going to change concavity. That's when we're going to have a point of inflection. When does F change direction? At x equals -3, 3, and 6. I don't like to say when F changes direction, so I say that's when G double prime, which equals F prime, changes sign. Great. Easy, 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 easy. What's G of 12 and G of 0? Super easy. The test questions I gave my students this past year, a lot harder than this. G of 12 would be the accumulation from 6 to 12. You can't do the antiderivative of this function. It just makes sense to geometrically accumulate. This is an area of 9. That's my answer. And if I want G of 0, I would go from 6 to 0. And this area is just a half of a circle, radius 3. So it's 9 pi over 2. But since I'm going backwards, it'd be the opposite of what I would get from 0 to 6. Easy. Probably 2 points, 1 point for each of those. And then part D. I mean, this is another easy question because the answer has to be at x equals 0. And they didn't even ask you for the value, but whatever. You could have found the value easily because we found it last part. It has to be at x equals 0. Why? Because the derivative is negative from -6 to 0, and then the derivative is positive from 0 to 6 and 6 to 12. You could have said greater than or equal to 0 would have been counting. G prime is negative and positive and positive. I don't need to check all of my candidates. If you checked your candidates, great. I'm sure that's what your teacher taught you. However, in my class, we only check the candidates that we need to check because we've analyzed the signs of our derivative. The minimum had to be at 0, and this is why the minimum had to be at 0. I'm done. Cool? Moving on. Question number 5. Very much a straightforward, no calculator motion question. 2 particles, you had an H and a J. H is the position. Maybe you didn't want to say x of h because it confuses you, so you change it to a p. Maybe you write x of h is equal to p of h, which is what I like to say in my class positions. And we wanted the velocity of h, so I'm going to just take the derivative of the position. And I have to use the chain rule. I have an O and an I, so I take the derivative of e to the t squared minus 4t, and I get e to the t squared minus 4t times 2t minus 4, and I plug in 1, and I don't simplify. Did they ask you, are we moving left or right? Nope. You would have said we're moving left. E to any power is always positive. Did they ask you if you're going towards or away from the origin? Nope. They didn't ask you about any of that. They just asked you for the velocity. Soft. Hopefully we did well. When are H and J moving opposite directions? We need to look at the velocities. We're going to see when the velocities are opposite of each other. If you just wrote that, like the velocity signs, you're looking at the velocity signs, you probably would have gotten a point. But what you had to do, which probably tripped up a lot of students, is take both velocities equations and set them equal to 0 and do a sign analysis. Now, maybe you didn't practice this. My students didn't practice this. They practice straight line motion questions. But e to any power is always going to be positive, which means, this is a half. Which means this is to the left of this. I just made a mistake. I just noticed. Which means the signs are going to change. Add a half. If I plugged in something like 0, this will be positive, this will be negative. So I got negatives. So that means my position's decreasing. If I plug in something like 1, this will be positive. So my answer is not this. My answer is a half to 1, as that's when velocity signs are opposite. This one, it's probably easy to look at 0, 1, and -1. And to look at the signs, if you plug in 0, you get negatives. If you plug in like a half, you get a positive, you get a negative, you get negatives here. So when your signs are opposite, that's when you're going to, wait, it's 2x minus 4. Is this, what's going on? Did this just like hide on me? 2t minus 4? It is 2. I'm wrong. I was wrong. I was right the first time. My bad. This is at 2, and this is at 1. This question is, maybe a little tricky, but overall pretty soft. There has not been one question that I have been stumped on. There has not been one question that I have been like, oh, that's tricky. Oh, I haven't seen this before. Everything I've seen so far, I have seen before. Particles move in opposite directions from 1 to 2 as velocity signs are opposite. Part C, they're even telling you guys, hey, look, the derivative of Vj is positive. So maybe you need to say that V prime of J is the acceleration of J. Maybe you say that. They ask you for the speed of the particle, J, at time 2. Well, all you have to do is plug in 2 into the velocity of J to figure out that it's positive. Did you have to find the velocity? No. All you have to do is check that it's positive. Well, if the acceleration is positive and the velocity is positive, speed's increasing. This is the easiest speed question ever. Things that make sense, like positive and increasing, you're speeding up. Uh, Usually they like to ask when like acceleration's positive, but velocity is negative, which means your speed is decreasing because your velocity values are getting closer to zero. But nope, not very challenging. Um, if you just said it's increasing because the acceleration is positive, that would have been not sufficient. You needed to check your velocity value first. So probably the only part to this question that was tricky is making sure you checked your velocity value. You didn't need to find the value. Part D was a good question. You had to be able to take an antiderivative. And this antiderivative, you had to use U substitution or just figure it out. I hope you figured it out. It's actually not that bad. You should have noticed that there's a composition. Now, since I don't have a calculator, I'm not going to accumulate. I'm just going to take the antiderivative and find C. Okay. If I can take the antiderivative and find C, like do it. But I use U substitution to take the antiderivative to get the position function. I have a velocity, take the antiderivative, you get a position. And you could have, I think, figured out that the antiderivative of the position was 1/4 t squared minus 1 to the fourth. Imagine the 4 coming down. This would turn into a 3, and then I'd have t squared minus 1 times 2t. Okay? Like that could have been figured out intuitively because the derivative of the inside is on the outside. If you use U substitution, you would have found that the 2t's canceled. You had U cubed, whose antiderivative you take. You plug in 0.7 and you get a C value, which is not the nicest, but not horrible. This is 28 fourths minus 1/4, which is 27 fourths. And all you need to do is plug in 2 and just call it a day. If you wanted to, you could have used the fundamental theorem of calculus, like the application of the fundamental theorem of calculus, to say an unknown position is equal to a starting position plus a displacement or accumulation of the derivative. You could have done P of 2 minus P of 0, and you wouldn't have worried about the C, and you would have had 7 plus this value, which 3/4 divided by 4. Yeah, it would have worked out, I'm sure. Because when I plugged in 0, I would have gotten that value. So yeah. Anyways, just making sure you have the correct antiderivative is an important part, and either finding C or plugging in this and not worrying about C. Let me just show that just so we know. This would be 7 plus 1/4 3 to the fourth, but then minus, it would have been 1/4 negative 1 to the fourth. And this and that combined would have given you the C, which is what I did. Okay, again, not too hard, but yeah, use substitution. You got to know how to do it. Then we go to 6, and if you're my student, you were ready for this implicit derivative question. It's been showing up the last 3 years. This is the 4th year in a row, I think, where implicit derivatives have shown up more and more frequently. It's a first semester free response question. We got to be able to take a derivative implicitly. Whenever you take the derivative of y, you got dy dx, but there's no product rule yet. There's no chain rule. There's no distribution of a negative. You subtract the 1/2 x, you factor out the dy dx. The only thing that might have been tricky was to multiply by 2 to see that it's negative x and 6y squared minus 4y minus 2, and then having the negative, forgot again. Let's look at question number 5. Let's look at question number 6. Great. Very, very standard. There's a point on the curve. I put this in like one part of my free response questions in the class, and we're using it to approximate an x coordinate. All you needed to do is to plug in 2, -1 into your derivative, use an equation of a tangent line. Don't even simplify, plug in 1.6 into it. Very easy if you know like the basics of calculus. Vertical tangents, classic question for implicit derivatives. You take the denominator, you set it equal to 0, but look at what we have in store for you. We have something that is a quadratic whose a is not 1. I don't see it often, and you don't see it in my class often, but there it is. Hope you remembered how to factor. You're only looking at y's that are positive, though, so you could have actually figured out that y was 1 and like guessed and figured it out. If you like added 1 and been like 3y squared minus 2y, oh, y has to be 1. Once you get that y equals 1, you plug it into your original equation, and you get that x is equal to simply 2. It's like such an easy question. Could have been a lot harder. Usually with vertical tangents, we've in past years like had an equation that we've plugged into our original equation. So we like had x's and y's, and we like solve for y and we plug it in. But here you just get y equals 1. You don't really care about the -1/3 because y's are positive. Plug it into the original, add 1, multiply by 4, square root, done. And then the last question of the test was a very standard implicit derivative, but it's a related rate. You're taking a derivative with respect to t of a new equation. So this question, you actually ignore this. We take the derivative, paying attention to the fact that this is a product. We need the product rule, derivative of the first times the second plus the derivative of the second times the first. The derivative of log y, 1 over y. And whenever we take the derivative of x, it's dx dt. Take the derivative of y, it's dy dt. Take the derivative of log y, it's 1 over y, dy dt. Plug in x is 4, y is 1, dx dt is 3. Solve for dy dt, and you get -2/3. Overall, team, I thought this test was fairly soft, very straightforward. Maybe it's because it was on the computer for the first time. I heard the multiple choice was harder this year than expected, and maybe the free response was earlier. Maybe they're trying to get the multiple choice and free response results to be more in line, because in the past, multiple choice is better performing than free response. So we'll see. Does that mean I, as myself, need to focus more on multiple choice in the second semester? Probably. Maybe I need to push multiple choice more. Free response is the difference maker for sure, but these free response questions pretty darn easy. Okay. Hit me up with a comment if you think I did anything wrong, but this is right, I think. Peace, Calc students.